having me back. I have 50 to 60 minutes of things that I want to share with you. And this is slightly different format than some of my typical presentations because it's very command line driven. But what I want to show you is actually kind of an abstract concept. So I have a real dissonance that's playing here. And the reason that I want to bring this to the Java users group, there's actually little in terms of Java syntax, is that the Git tooling has become, even in the last couple of months, ever more important to Java people. It is, in fact, we ran some statistics the other day. My colleagues are with me here from GitHub, and we ran some stats the other day. And Java is just off the charts in all of our repos. We ran some site-wide statistics. And the other piece that goes along with this is Eclipse is now 60% moved over as a foundation over to Git as a repository. So in fact, this tool is everywhere in the Java ecosystem. And what I'd like to do is actually take an opportunity to kind of step back to computer science, kind of all the way back to, dare I even say, your university or kind of deep technical level training, and tell you a little bit about how this system is constructed so as to make the day-to-day usage far less intimidating. I have very little that I want to say about myself. I like to keep this as low-key as possible. I'm Matthew McCullough. I work for GitHub, which I certainly believe is the best job on the planet. And the thing that I am here to talk to you about involves both the GitHub system, but more this evening focused on the Git tooling. When you bring Git into an organization, you'll often bring up the README at some point, at which point, if it's not utterly rejected by the mere fact that someone would put this kind of thing into the README for a product, you then win, because you get to use the best version control system that I've ever used in my career. I've only worked for GitHub here in this calendar year, but yet I've taught Git for 5 years, and for much of my 15 years of doing Java software development, that is who I am at the core, I've really struggled with version control because it's been one of those things that's supposed to enable you to do more stuff, but it's often been the thing that's held us back. That changed when I started to use Git. And one of the things that it enabled is a massive amount of collaboration. This is a graph that I actually don't believe has been shown publicly before. This is a contribution graph from last week, and this is github.com being built. And these are the simultaneous actions of the people on our team. This graph has been partly public for a week or two now, and this is the number of deploys and commits that we do. And you say, what does this have to do with the technology that you're actually showing us? But this is really the product of what using Git gives you. Collaboration, ease of deployment, all these flexible build and kind of work models. But I want to go to the opposite end of the spectrum because it's rare that you actually get the opportunity to do so. We often treat programming as this ultimately simplistic kind of activity that simply is just sitting in front and making sure you type the right sequence of characters. But there's an awful lot of math and science to this, and that's the hat that begins right now. So here's the beginning of all of this. We use a centralized version control system, and in that we get the simplicity of a database giving us a monotonically increasing revision number, R1, 2, 3, 4. You may have even heard me use that line before. But when we switch to Git, we use a hash of the content itself. I often say to people who are new to this domain that it's an easy way to think about it is that it's a fingerprint. It's an identifier for the content inside the file, inside the folders, inside the commit, and also for tags. 4 primary things that are hashed here. Now these 40 hex characters are, on the surface, if you were to just treat them as this thing that you have to refer to and reference, terrible. Horrible to actually cope with if you are talking to colleagues and trying to use this as the means of, how are you coming on 9AB223? It's impractical to say the least. Now, what they represent is extremely useful, and what I need to give you is a bridge between this unwieldy number space and something that's manageable to hand from person to person. Now, this digest on the content is globally unique. For all intents and purposes, physicists would even agree that 2 to the 160th power, which is our number space for this, is a globally unique identifier. So we'll treat it as such for the rest of the talk. Now, you see that thing, and you can imagine with me teaching introductory classes to Git that after you show this slide, half the class leaves, and the ones who stay cannot believe that this is the new way that we identify individual commits. Neither can I. Neither could I until I saw the science behind it. We are going to create a Git repository without ever using Git commands, and I believe this will give you a newfound understanding for the system. We are going to head over to our terminal window, where we're going to do our bit of coding tonight, and I'm going to git init project 1. Now you say, wait a minute, you claimed you were not going to use Git to actually initialize this, but hold on, I'll be truthful about this. I'm going to show you what's in this .git directory so that this little setup of a set of folders and directories will have no real impact on what we create for our commits and our content. The piece that I'm most interested in, this is the .git directory that I'm showing you, the thing that contains the version-controlled objects that we're going to write. At the moment, it has this objects directory that is empty, info and pack, two small directories beneath there, but no files whatsoever. And I'm going to continue to repeat to run this tree command, and we're going to look what appears in that objects directory and make sense of it. So our next step is where I actually get to eschew using anything about Git at all. We are going to write some content to a file. So I'm going to do just a simple echo, and we're going to wrap it in quotes, and we're going to very carefully make sure that our capitalization and everything is just as it should be, and we're going to write it to a specially named file over here that we call hello.txt. Now, having written that file to disk, Git does not yet know anything about it. And what I need to do is simply use the git add command, which causes that to be digested. We're taking kind of a layered approach here, using Git a little bit and soon enough not using Git at all, to add that to version control. But what does that really mean? That means that if I show you the .git directory once again, that we have taken the content of that file and run it through the SHA-1 digest function and determined that the individual fingerprint for that file's content is 557DB03DE997. OK. All right, what is this folder? What does this thing actually represent over here? What's written out to the directory? Well, I can show you. I can list that file. That's now preserved, but I can also manually recreate this same set of structure. Now I'm going to go one more level further with a git commit, so we'll have two more objects created in this directory. That one represents the file's content. Next, we need to represent the directory and then also the commit, the action, the transaction, the wrapper, the shell that sits around side the folders and the files beneath it. We're going to supply a commit message over here, and we're going to carefully type it as first hello, exactly like so. And this commit that we've now made has saved a couple more files that you'll see with the tree.git directory. We now have three of them, one for the file, one for the folder, and one for the commit that represents the transaction that encompasses both of those previous two steps. Now, we've written this to disk, and the next step that I think is a lot of fun to show off is to actually take and run the contents of a little string over here, a specially formatted string, over through a command line tool that produces that same hash code. Now, on this line of code, I'm not running a git function anymore. And yet, if you do a little bit of comparison over here for just a second, and look at the content, I see 7F, and I see 04, Echo, Delta, Charlie, so on. I see the same kind of identifier that I saw when we actually wrote this out to disk. Now, this printf that we just did here, this blob, this 12-digit hello world with a character at the very end, is actually giving us a few bits of information that are also in those encapsulated pieces in the objects directory. This is the type of thing that was written to disk. A blob means a singular file. Git doesn't actually have a mode for binary versus text. Everything it writes is simply just a blob. The next is the number of bytes. And you say, well, we could read that by actually looking at the contents of the file. But it's an optimization that it actually stores the length at the time that it writes it. It's kind of a cheat, a shortcut, if you will. And then we actually have our null byte over here, our actual characters, and a null terminator on the same. And running it through this function, running it through this digest over here, has provided us a means of, without Git, calculating SHA-1 hash codes. Now, given that we've run that through, we have a question of matching that up with the exact content, the hello world and the file and directory structure that we had created before. Well, I'll do this. I'm going to actually route some content in from standard in, kind of cheating halfway between this gitless and the Git form that I used from before. I'm actually just going to take an echo statement in this case, and I'm going to put hello world over here with a little improvement to the quotes. My shell could be slightly unhappy with that particular choice of quotes. And we're going to get hash object dash w, and we're going to say that we're going to get the content from standard in. Now, some of these modes, you wonder, why would Git actually provide this low-level function, which it appropriately by strata, by layer, calls the plumbing. There's the porcelain on the top, the user-facing functions, and the plumbing, the ones that function beneath it. Well, this plumbing piece over here allows us to actually write the object to disk, and dash standard in this case, says get the content from what I'm piping from that first shell function there. So when I run this instruction over here, when I've got, let me make sure I've got my standard in and all of my quotes appropriately as they should be. We're writing this out to disk, running this, but wait a minute. I am clearly missing something, and I'm missing a dash over here at the very end, dash dash standard in, much better than our m dash that appeared. There we go. So finally, we've produced from an echo stream the ability to write one of these same files, this 5.5 that we're getting here on our disk. Now, what did this do to our tree of .git? So far, we're just kind of feeling our way around. We're feeling the walls, kind of seeing what we can see. But wait a minute. That 5.5.7 delta baker was already there. And you saw that this produced exactly the same output when I wrote it. So what we've now done is show that Git actually doesn't have any magical recipe. It's not a specific flavor or an incantation that the tool itself came up with. What we've discovered, the first little layer that we've peeled back, is that you can actually just use standard commands like echo, or even build your own kind of a conglomerate function with SHA, and you can digest the contents of these strings and end up with these unique fingerprints. That's the thing that we want to kind of recognize at this point. You can produce these fingerprints just from the contents of strings or the contents of bytes. Now, given that we've gone all the way into that, and we now said it's written to disk, and we've kind of seen even where it is in the file and folder structure, could we just read this back from disk? I mean, could I take the cat function and just read back into the 5.5.7 delta baker directory file over here? Could I read that back to screen? Well, that does not look quite like what I expected. It's not as naked or as exposed as the other layers that I've shown. So what happened here? Well, what we actually got in this case was some zlib compression of the file that was in that directory. But you know what? We can actually set up our own little Perl alias and get the same kind of thing to be able to decompress in the absence of Git. I can set up an alias over here with a Perl mcompress zlib what? Well, a little Perl function that I'm defining. The second will actually be a little bit clearer. What I'd like to do as the second step to this is to have it deflate. That's the little program that I just set up here before. You're using Perl. Well, I wanted to be polyglot this evening. So I now am able to deflate the object that's hanging in this directory. I hope ever so slowly it's becoming just a little bit and a little bit and a little bit clearer how these are put together. Just a little bit at a time, it's starting to sharpen. That these things are just decompressed or compressed strings that we can deflate that have, and look at that pattern, you recognize that from a few minutes ago, blob 12 hello world. Do you remember that? You're starting to be able to put the threads of these pieces together. You thought they were kind of scattered all over, and you're starting to see the same thing show up and show up. Oh, so it's just a what is it with the byte count and the content in the file, correct? And the file name itself is the fingerprint of the unique content, correct? And the first 2 characters of those 40 characters are the directory name, and the remaining 38 characters are just the file name itself. Done. I've literally explained how every Git commit works, and the only thing that I've left opaque at all in all of this is actually just the compression library itself. You could even install your own zlib command line utilities. You could use this from Ruby. There's Java equivalents to the same. But that's even the only small piece that I've left, and it simply looks like zip compression as you're putting it into out of that file for a little bit of efficiency as you write it to disk. Now that we've seen that piece, I actually want to go one step a little bit further and say, well, then how would Git actually write out the tree, the next most important piece here? Well, that would be done through another plumbing command called update index. We can say update the index, add cache info, a Unix file permission over here, 644, we recognize that, 100, a normal file in Git, and then we have over here the hash of the file that was already calculated and the file name. Now, why does it matter that we write it in this form, and why does it matter that when we're writing the directory, the tree, the folder that our source code is contained in, why do we supply the file name and the hash then? Well, this takes us, for our first time, actually back over to slides for just a minute, because everything that we've done so far can be turned back into what I believe is a very, very helpful picture of the data structure itself. As we're building these things from top to bottom, and some of you may have already seen a graph or a picture like this that I use often in my talks, we calculated a digest of the file's contents. But what you saw at the lowest level possible is that the file name actually didn't matter at all at the time that the file's content was written to disk. This is one portion of Git's efficiency, and that if you copied and pasted the exact contents of a file, it really only gets written to disk once, but then gets pointed to by any number of directories that happen to use that content. You saw that firsthand because there was no remnant of the file name itself in the first little object that we wrote. It was in, wait a minute, let's go back to it to be doubly sure. It was over when we were writing the directory names that we actually assigned content to be paired up with a file name. It was at this level that those two things were finally glued together. Back to the picture again, as we start to build this up, the picture has exactly the same concepts up here. We have the type and the hash and the file name stored at the tree level, which we commonly say is the same as a directory. And these things, of course, can be nested one beneath another all the way until we get up to the level of a commit. This is not a var args field at the top. It is a singular field for the top level tree that it points to. The parents are a var arg field. You can have more than one parent. That's a merge. But in this case, the tree, the file in the folder system, is a singular field. It can only point to one. And this is why the .git directory lives in the top of your project structure. That is the singular directory that captures everything else beneath it. It has to be one at the top of the pyramid. That's pointed to by each and every commit, but the commit's hash itself is what? Since we've been looking at the constituent parts, the composition of the commit is a pointer to the tree, so it knows what content, what files, what file names belong in there, but also a pointer to parents, also encapsulating the content of the author and the committer as separate fields, and the commit message itself. It's all of these pieces glommed into the final little bit at the top of the tree. If we look at our tree of .git again, does Git actually give you any useful commands that you can go at and kind of act on those things without whipping up Ruby or Perl or JavaScript to actually touch those? Of course it does. And I actually think that you'll find a reasonable use case for these in your day-to-day use of Git. Git provides a function called cat file. So now we're getting back to kind of on the fringe of a useful utility, back out of the land of computer science, back to a practical sense. And cat file can actually serve you reasonably well. If somebody gave you a hash of the last deployment to the site, and let's say that we happen to know that we could get a list, git log -1, oh, 4f delta 10, that's our most recent commits ID, that we can get cat file and ask it what type is 4f delta 1 in this case, and it says, why Matthew, that is a commit. And I say, okay, I'm going to repeat the same instruction, and this time, cat file, I'd like you to give me the contents of that particular file that I'm reading from the objects directory. And the result is Oh, it's funny how that matches up exactly with the diagram. A pointer to the tree, the author, the committer, and the commit message. You're now viewing the composition of these individual parts that are calculated as that hashed sum for the commit. Now that we have a pointer to the tree, do you remember tree.get? Do you remember that 97 Baker 4? We just saw that as a result of running that instruction, 97 Baker 4. Let's try to repeat the same thing. Let's ask it what the type is of 97 Baker 4. That should be sufficient. Oh, that's a tree. Well, no surprise there. You already knew that before running the instruction. But we are interested in what the content of it is, and here is where that information was captured when we did the write tree. It's got the mode over there, the 100 representing a standard file, 644 being the user write and other read privileges on the file, blob being that it's a file, it doesn't care if it's text or image, it's a blob, not a tree or a commit. There's the identifier of the content itself, and there's the representation of the file name at the end of the line. There's all your pieces put together in a way that you might never have gone down to the bottom of this kind of stack, but it really seems kind of simple in hindsight. It's just composition of files, folders, and commits, each with their unique identifiers at each level of this data structure. Now that we've kind of built this out piece by piece, there's an interesting take on this of, well, what do I do with it, though? I have this knowledge, and maybe it's kind of computer science, but what basis does this give me for using Git, for using it better, for trusting it more, for perhaps even switching to it? Well, now that you've seen these three pieces, I think this example that I often use of damaging a repository becomes a lot more meaningful. I'm going to copy recursively here for just a second the project 1 that we were just working on, and I'm going to call it project 1 damaged. I'm going to go into this damaged repository. It's not damaged yet, but we're going to soon do our work on it. And we're going to, once again, for the sake of reminding you, look at that most recent hash, 4F delta 10. Git status is very happy. Git log is very happy. It's showing me the commits over here. But I'm going to take vi and go into the .git directory and over into the objects folder and over into 4F and complete the file name. And at the very front of this, insert a character that effectively makes it incongruent, incomplete, unhappy. And so I'm going to write that out to disk, and then I'm going to drop back to the command prompt having written a new character into that file, and I will run git status, at which point it says, no, you don't. This repository is no longer valid. Now, I did that on an extremely small one with just one commit. It's very shallow, but that made the example nice and simple and clear. But the same thing has value on a large repository with a great deal of history. You can run git fsck to actually do a file system check on that repository. And with a few option switches, you can actually have it recalculate everything, both with the full and if you want to change the rule set so that it doesn't allow some of the older misbehavior that was present in some ancient editions of Git, you can also have it be strict about the things that it finds. You could even set this up on a cron job if you like. We have this as part of some of the back-end infrastructure at GitHub. But this is the kind of thing that you could run on your own repositories. You could set up your own job to health check them. And this is giving you a guarantee. I think it's almost hard to figure out how much value this is. This is giving you a guarantee that every bit of every commit ever written to the repository from the beginning of time until now is in its proper place without any bit rot or malicious manipulation. This is making sure that all those checksums recalculated back from oldest to newest still all match up. And you know how that happens because they're simply just linked one to another. You saw that top to bottom picture of a single commit, but then how would a commit be linked to its neighbor? The answer is incredibly simple. The next commit, the very first one, has a special marker in the parent field called nil, but all the subsequent ones past that inception original commit point to their neighbor. And this linkage from one to the next would be damaged, would be broken, and in a way that you can't really trick it to match back up. If you write content, you say, well, wait a minute. I'll take one of the .java files and I'll put some sort of backdoor into it. But remember, when it runs the SHA function, you're not controlling the output. That's a fingerprint of the content. So Drats, you can't control what the fingerprint will be there. And the fingerprint gets written into the tree directory and into the tree data structure that represents the directory. And when that is SHA-summed, it's a listing of all the content beneath it. So that will then turn out to be a different hash if you made even the slightest change to the file. And that will propagate all the way up until it breaks the linkages between these, because the hash of the commit is based on the hash of the tree, is based on the hash of the files, and you simply cannot maliciously craft in a reasonable amount of time a file that would be a replacement for the existing one with, say, a backdoor placed in. That is a very fascinating thing that it gives you, but this is kind of what you get for free. What do you actually get as far as workflow and behavior from all of this manipulation of commits and trees and the merges that we often do as part of a software development process? Well, some things that were increasingly hard as the team scale grew and grew in a version control system are incredibly easy here, because they're baked into the data structure, which is why I feel completely comfortable saying there's value in knowing how it works. When you have divergent branches, you're working on a feature and the main branch at the same time, the master branch, and you go to merge those back together, you often don't stop to think, how is it finding what actually needs to be merged? But the answer here is baked into the data structure simply to the point that we say it is finding where these two commits have, this commit and this one, the same parent. In fact, I can genericize that statement to say the merge base is where two commits have the same parent hash, the same identifier. That was where they both had the same common ancestor, and that's where they started to diverge two different directions. In fact, if we try this from the command line, you say, is that visible? I mean, is that just something that you're showing us, or is that something that you can actually see from the command line? You can see it quite well. If I do a get branch over here, and I go back into the healthy repository instead, that will be a wise choice on my part, I will clear off the screen and start a get branch that I'll call feature number 1 over here to the side. And having created that branch, so I've got a feature 1 branch that's hanging off to the side. Let me show you the list of those branch names there, like so. And now that I've got the split, I'll make some random changes on each of these two. I'll do 2 random master branch changes, like so. And I'll get checkout over to the feature 1 branch, and I'll do 2 more feature.txt changes. Now, I'll visualize what's going on here with those two. We've now got 2 arms splitting in different directions. Now, I am on currently the feature 1 branch, and I could ask it in very simple form, Git, please give me the, and yes, merge base is a top-level command, give me the merge base of this and say master, I guess. And well, what are we trying to actually do here? Well, wait a minute, that's insufficient. I need to give it 2 arms for it to consider. What is the merge base between, master and let's say feature 1? We're actually giving it 2 inputs. And I'll relate this to how you type the merge command in just a second. But look at that. There's the common, that simple algorithm being run. Race backwards from these 2 points until you find a commit where both on these 2 race tracks are pointing at the same common ancestor, end of algorithm, end of loop. That now gives us a really clean graph as to what could potentially be merged together and is a basis for why Git is easier at merge time. You're not supplying a long list of revision numbers, and in fact, you never really, for people who are using Git at their jobs, have to type this. This is happening for you at the time that you perhaps git checkout master branch and git merge in something like feature 1. People often think, well, it always has kind of a context sensitivity when I type a git merge command, and you're right. In fact, it's kind of like that merge base where I ended up having to supply 2 parameters instead of 1. This is saying, well, I'm going to assume the one you're on because I need a current working directory in case there's conflicts or things you have to resolve. So I'll simply, for an optimization reason, just have you supply the other branch that you need to merge in. But what is less commonly known is that you can supply as many branches as you like here. Wait a minute, that seems to complicate things. But no, it doesn't. because the algorithm that I just described scales perfectly well. Walk back the paths on all the branches given until we find a common ancestor for all of them. It simply is a couple more checks, 2 more checks in this case, but the algorithm remains absolutely consistent. It's just how many arms that we're checking at each point in time. And I think there's almost a comfort level in knowing that it's not quite as fancy or as black box that you might have assumed. It's a pretty simple algorithm that produces a pretty simple outcome, which means a lot more automatic merges that we don't have to deal with in terms of conflicts. If we can describe these things in terms of these kind of soft reference names, these pointers to branches, to tags, what more could you possibly derive from this? Well, in fact, I'll show you something that I've actually never seen in a presentation before in terms of Git syntax, but has been present for quite some time. You all may know the very basics of commitish and treeish, but now, rather than laughing at these names, you'll actually know where they derive from, because the 2 things that I showed you we wrote, the 3 actually, are the blobs, the trees, and the commits. So you see that these are just reference and notations for pointing at these long, remember, annoyingly long 40 hex character identifiers. So why was I able to get away with using as little as 4 in these cases? Well, in fact, this causes me to introduce one more command to your vocabulary. Inside almost every Git command is a first run at revparse before it runs what you asked it to do. Revparse takes any kind of short hash, let's say like the 4 franc delta 1 that we had from before, and turns it into its nice globally unique identifier. Most programs, kind of in the same way that we might reference variable names and those being translated to memory addresses, that was a human convenience that we could give it a friendly name or some small part of the identifier. This is ultimately what the system, the code, actually wants for referring to any given commit. So in fact, whether you're running merge, whether you're running cherry pick, whether you're running show or log or even rebase, it is turning your short hashes, your friendly names for branches and tags and small little bits of commitish like this into their long counterpart as the very first step. Now, there's got to be some sort of compromise, it seems like, between this shorthand form and the longhand form, especially if you're going to start kind of describing and passing it around and also giving some relative position, because you don't want to be pedantic about having to apply a tag of I just left my computer for coffee, number 21 for the time of the day. That's just unreasonable to expect you to put a tag every time that you walk away. So there's a git instruction that actually helps out a lot with this. I'm going to generate a few more commits, generate some random changes of 2 more for more sample2 txt files like so, and I'm going to ask Git to please describe the most recent commit. This describe command is actually really pretty helpful, because what it actually does is walks back on the graph and finds the nearest annotated tag that points to this and then gives you a relative position to that tag. But what I seem to get is a complaint about this that didn't seem to give me anything helpful at all. There are 3 modes for tags, and one of the benefits that I'd like to see you walk out of with here tonight is that that tag that I ran just a moment ago is probably something that you start using a lot less after tonight's presentation. There is an equivalent tag command with the -a that I would assume should become your default. This is an annotated tag, and to be honest, it's really more a real tag than the one without the flag is. An annotated tag is a first-class citizen. And in fact, it would be helpful if I'm going to Control-C and not write that output. And I'm going to get gc to garbage collect my objects directory. I'm going to tree my .git objects folder to show you what I have hanging in there for the moment. I want to show you a before and an after. I want to run a normal tag, so we'll just say normal tag right here. And I'll run that tree of .git objects directory again, and there's no change before and after. I wrote a tag, but nothing got written into the objects directory. Why? Because the form of tag that the default writes is just a pointer to an existing hash, but it doesn't have any of the integrity, the contents, the who, the what, the when, the where of a normal commit. An annotated tag, the one that I was trying to run prior to that, git tag-a, stands for annotated, is actually writing an object. So we'll say, in this case, sample with annotated, like so. And having done that one, what you'll find is that up pops my commit message editor. This is my place to be able to type, this is a tag to show to my SFO jug friends, and save and close. And the before and after is what you're supposed to take note of in this case. Now you see that an object was actually written to that objects directory. This is what I consider to be my go-to tag command, because inside here, wait a minute, are you telling me this would actually work? Remember that thing that we used before? Dash type T, could I ask it what 0188 happens to be? Yes, I can, and it tells me it's a tag. Well then, could I ask it what the contents of that tag is? Why, absolutely you could. There's an object, a type, a tag, a tagger who did it, and then lastly the commit message. And now that looks an awful lot like the commit that you saw from a while ago. It is in fact about the same as the commit writing code, but the only thing that is missing over here is it doesn't point to a tree. Why not? Because the tree is already preserved in this commit. We have the state already saved. We want to point at an existing state and to describe why we got to that state. We cut a release. We were rolling back. That was a trial run that we pushed out to production. That's what a tag's purpose serves. So it is an indirection to point over at an existing commit. When we ask git rev parse, we're starting to glue these commands back together. If it would be able to tell us anything about sample with annotated, it of course converts it over into the first class citizen, like so. But if I were talking about one of those other tags from before, so let's see, what other one? I just, like this tag like that actually points at the commit itself. Let me say that once again. The rev parse of the annotated tag says, here is your actual tag object, because there is such a thing in the .getObjects directory. The rev parse of this other lighter weight, dare I even say of minimal use tag form, is actually pointing over at the actual commit. Wait a minute, can you prove that to us? Of course, by going right back over to cat file again. Please show me the type of delta 22 Charlie. You're seeing that number come from the bottom little element there. Ah, indeed, that's a commit. Whereas if I tried to do the same thing on the 0188, but you already knew that, that's actually pointing at a tag. So what I think this helps you do is take all of this stuff that's happening beneath. I find that people use Git far more effectively when there's a sense, even if it's not your daily knowledge, even if you have to flip back to the slide deck, it seems a lot less special or amazing as to what's happening beneath. It's simple file manipulation, and you can, in fact, with the file system, see exactly where it's writing these things. Now you say, well, that's one small tangible bit to this, but I think it really, really gives you a grounding in the language of this tree-ish and commit-ish that you can use to navigate this graph. The caret is the most common navigation character that we teach in early classes on this kind of thing with Git, because that's one commit back. So you now remember that the data structure is a linked list, so we just start at the end, or whatever place we've identified, and go one step prior, or 2 steps prior. But that's pretty tedious, so we could go 5 steps prior, changing that symbol over to a tilde rather than repeating that caret symbol. We can also use the same thing to constrain 2 elements in the graph. So you could say, I'm interested from here to here. And you could certainly supply these unique identifiers, and they're going to be rev parsed into their full piece. But you could also use a tag and a tag. Or you could even use a branch and a branch as any of these 2 places, because ultimately, they're all the same thing. They're just pointers to nodes in a graph, and you're talking about walking each of the steps between these 2 points. In fact, that's what a lot of Git operations are, is here's a starting point, here's an ending, find the shortest path between the 2, walk. Done. End of algorithm in many of those cases. We also have some nice symbolic words, things like head, that also can be combined with caret operators, tilde operators, and then can be mixed and matched even to the point that you have the prior as part of a range. We have the branch names. We can merge. We can also use those symbols with the branch names, and we can do it longhand or shorthand. We can use longhand like that, but Git doesn't make us write that. It'll allow us to use the shorthand of things like this. Why? Can we be sure that it's pointing at the same thing? Well, in fact, if I have a remote repository, this can turn out to be quite useful. If I do something like a git clone of git@github.com GitHub training /hello git world, like so, and clone this down to my local disk. So there we go. We just retrieved a whole repository. I can ask it to get ls files and see what I have here locally and see a listing of those. And for any of those files, I could get at the hash of those. I could also get a listing of my branch names. And if I turn on things like verbose, I start to see these identifiers and start to think, oh, so maybe rather than being annoyed by the precision of these 40 hex character codes, I can say that it's a little less ambiguous than the human-friendly names like master. Git ls remote, which will show me all of the remote heads pointed to by this repository, all these pull requests, all these branches that were created. Let's try that again, piped through more this time, and do a little contrast and comparison with the master branch that we were on before. I see bisect, feature, master, gh pages, 8 dog 80 in this case. And you see this is ls remote command is asking the GitHub upstream side of the repository what that identifier happens to be. And I could ask that same simple question of my local repository over here. Git, what is the most recent commit? We'll do a branch -v. Or Git, could you tell me what the rev parse is of head? And every single thing is telling me exactly the same sequence of characters. And what I now get the confidence of this is when I see it on a remote identification, on a web page at GitHub, as a list of the branches, as a list of rev parse, well, this is all telling me that I have a globally unique number. I said I was going to literally treat it as such from a physics perspective that says the state of the entire repository on that branch and locally on this branch and the most recent commit from the current branch are all pointing at exactly the same thing. Now, there's got to be a little bit of a way to kind of mix and match and to kind of blend these two things together for some identification and some ability to navigate this. Here's some of that syntax that I said you're unlikely to have seen before, and now suddenly makes sense from a user perspective. This is legal to literally type out like that. I was typing cat file, and then I was looking at the most recent hash. Then I copied and pasted to get the hash of the tree, the directory structure and files that lived beneath it. But that's a common enough operation that we can do that just like so. Let's give it a try. The master's tree in this case. And let's do a comparison. Get cat file of -type for head. What did that provide? Oh, it's a commit. Let's look at -p. It says that the tree is Charlie 72466. So let's try our alternative approach to this. Let's do a git rev parse. Let's wrap it in a nice set of double or single quotes over here. And let's do a master and a caret with the wrapped brace of tree, like so, and a single tick at the end. Just contrast and compare. That's finding this commit's tree. I wanted to make that exceedingly clear before I press enter. And with now, suddenly all the surprise of the evening is diminishing towards the end. And maybe I should have turned the whole presentation on its head. But all of these things are seeming pedestrian now. Maybe even 45 minutes ago, they would have seemed crazy, confusing. And the more I repeat these and the more ways that I show you to come at the same thing, you're like, so they're all just 40 hex character identifiers of a state of the files or a state of the whole repo. And you've suddenly demystified almost everything about Git that has the potential to confuse you down the road. It's just states of the whole repo or states of the file system themselves. In fact, we can go even further with this. We can say, now that we've written a properly annotated tag, is there a way that we can refer to the most recent tag, but then some distance or position from that? Well, of course we can. Let's go back and try again and say, Git, please describe, as we tried before, the current head. And it says, no annotated tags can describe this as of yet. Ah, you're right. Now, can I describe, let's say, the master branch? What's the same outcome for this? You're right. That is true. I've got that same problem, the same difficulty. But what if I actually allowed it to use one of those non-annotated tags? That's what this option switch will do here. I'm actually going to place it more appropriately in the front, right before the branch name itself. And in this case, it says, oh, I'm now allowed to use these non-annotated tags, and I can create this hybrid syntax. That's what we've got, is hybrid syntax in which it takes an existing tag and melds it with a hash. Let me show you the list of tags that we have at our disposal. Now let me add another tag to this. Let me do a git tag -a -a of an annotated one, like so, and I'm going to apply this to one commit ago. That's where I'm going to put it in the graph. A good tag to be sure, save and close, and then try a git describe. We're going to try this again, of head, and of master, and there we have, in both cases, a hybrid identifier that's a little bit more human-friendly, but is still blended with that globally unique identifier. And I've actually found this to be a very reasonable thing to perhaps embed inside an about dialog, if you like. It's a little bit of both. It's kind of a human-friendly portion, as well as a machine identifiable piece.
When you did that tag, you did head ~1. Why back 1?
So as to give a little bit of a distance, because the git describe of the current branch, if I didn't put the tag farther back, would have nicely simplified just to the tag itself. Almost in a kind of way of smack, smack, Matthew, you dummy. You're on the tag, so there's no need to actually have any of the marker alongside it. What this provides you is, so that I don't have to be pedantic about applying tags, I can have one kind of drifting farther back in history that I applied, let's say, yesterday or the morning before, and it still will use that as a basis for me making more commits ahead. So kind of last street sign seen plus distance from street sign would be a very nice little way to kind of map that to an analogy. Sweet. So this is a very useful bit to embed inside, as I said before, your about dialogues. It's highly scriptable. You could just take the output of this and write something that captures and writes it over into a properties file. I've done exactly that on a Java project, and it worked really well. But what then you should be almost comfortable with, as soon as we ran it once, is this syntax. This should become part of your daily routine as well. You remember that recently somebody made a commit that said something about a variable name or a person or a particular type of change. There's a shorthand syntax for that. You can simply say git find me, log, rev parse, cat file, any of those instructions, and using this commitish notation that we've been talking about, say find me a commit that has those words embedded in them. You can even go further and say that you want it to refer to a specific file. So you can be more articulate. And this is kind of generic, of course, right? It could hit multiple things, so it finds the first one from the current point, working backwards because it's a linked list that points at the parents. But this is a little bit more precise. This allows us, rather than saying on a particular commit, rather than a generic commit, to say, you know what? On one particular commit, I'd like to read all the way down to the level of a file. Where does this become useful? I've seen people struggle or use graphical user interfaces to try to get an old copy of the file into the current directory, or even lighter weight than that, get an old copy of the file and just see it on screen. They'll use a GUI to go over to the right commit and then somehow display it in there, but that's accessible from here as well. Let's go back and look at our history with a git log -- stat to see where we've recently been. There's a travis.yaml file. There's a build.gradle file that I recently did. So what I could do is take a little bit of this hash identifier right here, copy that to my clipboard, and having embedded in my head the file structure, Git, could you show me the contents of that commit hash? Well, of course it can. But that's not what I want to see. I want to see one specific file in there. So I can simply just say at the end of that, build.gradle, and it dutifully outputs just that single one. This, again, is boring because it's demystified. because you now know that it's navigating through the graph to that certain point, and it's opening the tree, and it's looking for a file with that path, and it's doing a git cat file -p of that file's hash identifier's contents. Look back, look in, end of process. So many of these things that seemed like they might have been or could have been complicated are in fact very, very simple and straightforward as long as someone's actually stated what that recipe and process happens to be. Now for one that uses numbers where if I were king, I perhaps would not have put them in quite the syntax form, but here they are anyway. Let's say you're in a merge scenario. You're in the middle of a merge. The merge has not gone well. Perhaps you have a conflict. It says conflicted file. And you think, oh, I wanted to see the way it was and the merge, and I used the tool and it's wrong, and I'm like half-baked, but I don't want to roll it back with the merge abort. I just want to see the way the file used to be in the current staged area or in the common ancestor that was achieved by merge base, or the one that is the target on the current branch that you're on, or the one that you're bringing in, the source branch that you're folding over. This syntax within the file name at the end of it in the context of a merge is allowing you to see with like the git show command the contents of each of these by state. Let me repeat that again from the first one. You're in a merge. You have, let's say, a conflict. You're not yet complete with the merge. So there's a sense of what is the current staged file's contents? Maybe it's partly resolved. What is the one that was the common ancestor found by merge base, the place where the file had its inception, it split apart? Or the one on, you could even call it right and left, as many people do for the thought of a merge. Each of those has their own syntax for being uniquely identified. So now, all of this dialect, this dialogue, this ability to get at the files and the contents is really simply just a navigation language like anything else that we'd use in SQL or even lat-long coordinates. It just has some funny manipulators at this point. But does all of this actually help you be a better Git user? Absolutely. I've seen people, even with just a few of these things, like accessing the merge base or the right or left piece, go from, well, I've got to fire up a tool and get down to the right commit and make sure that I dig in and somehow copy and paste it and put it in another text editor, to simply being able to navigate back over here like we did with the build.gradle file and perhaps even just pipe that over to their favorite editor and pop it up like so. The time from typing that and getting it there versus watching anybody use a mouse to scroll is a real time saver, especially when you consider that that is repeated over and over and over again. And I think that that, with the difficult statement, means that we actually can return to our comfort zone of thinking of programming once again of something like this. I hope you enjoyed the demonstration. I hope that it was something different. That was the intent, and I thank you for your time. Thanks again. Thank you. I know it was kind of a nice little string of content, so my intent now is actually to take and repeat or clarify anything in this nice long string of stuff that you'd like me to do. I'll take questions and I'll repeat them and show off any demo that goes with this. The question was, as you're building up a Git graph of commits like this, we've got some commits, and we have branches off to the side, and then we decide at some point to perhaps rebase these. Well, those of us kind of in the know of how Git manipulates these things would say not that rebasing and these other activities are moving things around, but rather that it's making a copy of them and putting the new flavor of the branch, the arm, the series of commits somewhere else. Now, when it does this manipulation, the key, the thing that you care about, is that the label, let's call this over here feature 1 for this branch name over here, it is the label that's actually being moved around. When you, let's say, rebase, that's happening. And the garbage collection algorithm is simply looking for heads that have no human readable form of either a tag or a branch name. Those are the two qualifiers that make them eligible for living. It then proceeds to walk back the series of commits that's useless, that has no human readable name, that's useless, that has no human readable name, until it gets to a path that's kind of electrified, if you will, that is reachable, to use the more articulate term, that's reachable by some branch name that we do still know about. So it's actually really simple. It's walk commits that are no longer reachable by a human reference name, tag, or branch name. End of story. And I love that many of these things are simpler than maybe you thought they were, in a good way. Other hands? Other questions? Yes, sir. Let me jump back there.
Yeah, could you explain just briefly like a forward merge? Because we talked about a merge base, but not really a forward merge.
So let me try, but let me see if I'm getting it right. So at any point that I'm off the rails about what you're asking, have me start over or clarify. So I'm going to repeat, and I'm going to see if I understood it correctly. So here's 2 branches, and we're going to put some labels on these. We're going to talk about a feature branch, feature spelled funny, there we go, and a master branch up top. And we're going to talk about merging this back together in the traditional sense. That's our normal merge pattern. So when that occurs, what's actually happening, the question was, what is happening here, is that those 2 pieces are writing a new commit at the end of the graph. This is the default behavior for the recursively evaluated set of branches. And that commit simply stores 2 pointers. One is the identifier of the parent commit, that's kind of the primary branch, and then let's change the numbers up to kind of signify something that came over from the feature branch. So it's simply a node that points at the 2 ancestors that it brought together, plus any rectifying commit activity to resolve conflicts, the code that you help glue back together that didn't quite fit well. So let me stop there. Is that okay?
Sorry, can I ask one more question about it? So, and just I'm coming from the subversion universe, so if you're doing a merge like that, you could either be merging to the branch or merging back to the front. So what differentiates like whether you're merging to the branch or to the feature?
All right. So let me repeat this by starting with code to do this. So I'm going to clear off the screen here for a second. I'm on the master branch. I'm going to start a branch off to the side that I'm going to call feature 2. I'm going to generate a few random changes to master, generate 2 random changes on master. I'll show you what the difference is here, txt. And I'll git check out feature 2, and I'll likewise generate 2 random changes over here to the side. So this is feature txt. And if I git merge master into this branch, which happily goes, save, close, it's all happy, and all the way back down to, there we go, oops, projectors. Okay, let's come back over here. So now that we're back at our Scratch window, something a little funny going on with the projector there, but let's go back into our project that we were in. And we're on our feature 2 branch, and I just merged that. So I'm going to git show the most recent commit. And what you'll see is that there is an order sensitivity. So I'm answering the question by doing an example. There is an order sensitivity to the branch parents that are listed on a merge commit. The first one is the branch that we were currently on, kind of the destination in that case. And the second one is the one that was brought in, so the additive piece. So the order is what controls what from and what to. If we had merged the feature branch into the master branch, what you would have seen is the order of those 2 flipped. On the master branch would be a commit that listed itself, its own predecessor first, and then the incoming feature one as the second node. So order sensitive, sequence sensitive.
Why was that not fast forwarded?
Because I changed, there were simultaneous changes on both of the branches. Just to do a little bit of a quick little history run over here, history of the most recent tail minus most recent 5 commands over here. Wait a minute. Go like that. You'll see that what I did is I created the branch, and then I generated changes on master. Then I toggled to the previously created branch and generated more changes on the feature. So I was creating commits that caused them to diverge and then brought them back together. If master had been quiet, let's say, for example, you might have gotten the fast forward. Very, very good that you called that out.
Would you be able to publish that history that you've got right there as part of the presentation note?
Already done. It will end up in a gist less than an hour after this. So yes, I will publish the history for everything that I've typed this evening. I even have a cheat sheet that goes with this. So every little example that I did in Ruby and Perl and Python, you can copy and paste from. So yep. Yes, sir.
So can you draw a picture of like what the commit graph looks like for annotated versus the non-annotated text?
Yes. Yes, so let me repeat that by doing a picture over here. We have a commit graph. This is what we're starting off to answer the question. And we have some branches over on the side, so the same pattern that I've been setting up before. But what we effectively have is a box over here in which we can place tags. The question was around tags. Now, in this box over to the side, if I write a traditional tag, a non-annotated tag, what I have is a file, not a commit. So it would be inaccurate for me, since I'm using arrows as my commit thing here, to actually use this. What I'm going to do instead is say that it is a pointer back to some commit in the graph. It's an indirection that has a name that points at the already written thing. Now, this, to put a label on this box, we'll call this our it's actually called a reference tag, so we'll just call it a reference tag in that case. What would an annotated tag look like differently, though? It would be an actual commit in that box, an honest-to-goodness object sitting there, that in the inside of that commit has a reference to a particular commit. The other one was merely the indirection. The second one was who, what, when, where message plus the indirection back to the other piece. So let me start with a little text document over here to kind of outline both the question and the answer. Basically, I'm going to summarize as how does the pack file work. I don't like that it captures all the hashed objects. And please permit any typos. Let me do this, objects. And also, how would I get at something that is in a pack file? Well, to the latter piece, I can answer that it is just that same zlib compression that we used on the individual file. So you could use that same decompress function that we used during class on a pack file, and what you'd get is an output of directories and files that were the original constituents in the folder and file system. End. Nothing else unique, no more decomposition or digging into them. Now, each of those individual files, just as we did at the beginning of class, is still in turn individually compressed, so you might have one more step to go, but it is just a two-layer shell. The outer shell encompassing all the files and folders, and the inner ones exactly as we showed them in class. So using a Perl or Python or Ruby library would be the way to crack them open. But I want to not answer your question or answer it in a different direction with one other instruction over here. As I clear the screen for this history repository that we have over here, let me show you. Here's all of our history. And if I then git GC, which then garbage collects, and all of those things are now in a pack file, having run the garbage collection, I still can use any of these plumbing commands that we used tonight. I think this is very helpful to be able to see this. I can use any of the git cat file that we were using before, any of the git show against any particular hash. All of the fact that the files are now in the pack file, the compressed archive, or not in it, is completely hidden from you, so that all the vocabulary that I used this evening that are git commands will function whether or not it's inside or outside of a pack file. So what it provides you is this nice thin abstraction as to whether or not they're in there, and that would be your interface by which you programmed to getting stuff out of it. It'd be more consistent than writing your own compressed archives. Yes, sir. Basically, how do you get the confidence of getting kind of the golden copy that you had back in Subversion, knowing that the flavor that's up there is the same that everybody else has? And I think that answer is really, really easy. It is, as ugly as it sounds at first surface, it is compare hashes, because that is actually a stronger statement than you could have ever made in Subversion. You can mathematically, dare I even say physics, identify the state of everything that led up to there and say that someone else has every bit in exactly the same place in exactly the same state. So it's actually a stronger level of guarantee for the golden copy. So it is very reasonable in a build process and even in a deploy process to ask what the production hash is of the copy that's out there for a customer. And CI servers like Jenkins, for example, very popular in the Java space, will do an archive, and we'll do a MD5 or SHA-1-SUM, and you can do an archive command where it will keep track of those on the per build basis. And what's crazy is you can actually even put that in the manifest.mf if you like when it's writing the jars, and you can ask a production customer without any identifying information in the jar names. You can ask them this little tidbit of information and tell you when and who caused the build to be published by using the search function in Jenkins. I mean, I can tell you it was a button press by Jen on Friday at 5 p.m. by just that mere little tidbit of unique signature. And we all know, we've all done tech support at some part of our lives, even if it's for family and friends. The person on the other end will lie to you about what they're, it's on revision 6. Okay, check this file. It's on revision 6. I'm reading it right now. Yes, no, you're not. You're reading Delbert. But when they give you these unique identifiers, it kind of destroys that because they can't tell you a hash code that doesn't map to a build that you produced, or at least you can easily smell it out. It doesn't map to any build that you've ever seen come out of your system.
What I was thinking is more like initial setup. Is it probably the right idea is you do Git init, right? And then after that, you don't do any Git or check-in or whatever from that machine. You use something else.
Oh, as a hosting solution to have like the clean server copy of it. That's about the right idea. That's in fact what clicking the new button on GitHub does, is a git init of an empty repository with a -- bear on the server side.
What I don't like is when I was in that machine and I do git status, like I always say everything is deleted. You see what I mean, right?
But you can, -- bear is the option switch you're looking for. It means without a working directory, and so you can never actually make any changes there. It just becomes the recipient.
Git init -- bear.
Yep, that's the right vector. And I give free office hours every 2 weeks, so if you have any trouble, just come and I'll help you set it up too. And maybe one more.
Maybe this is a low-level question, but we were looking at the Git objects directory, and I noticed that all the directories were just a byte, and then like the longer part of the hash.
Yep.
Why 1 byte, why not 4? Can it be deep and recursive? Why is it flat like that?
So the balancing was kind of through a semi-scientific process of trying to figure out what file systems kind of liked. It's a compromise, to be sure, but of the 40 hex characters that are the SHA-1 digest, 40 hex characters, the first 2 are made as the folder name and the remaining 38 are the file, and that turned out to be happy on most file systems for creating balance. There are some file systems that do not like 1 million files in a single directory, and this was a very inexpensive way to not. Yeah, it's still true, depending on what kind of SAN storage you're putting it on and so on. The performance characteristics are pretty varied. There's some really anomalous performance curves of millions in a single directory.
I thought you no longer had to worry about that.
It's still a concern on some platforms. And remember, not everybody has the advantage of moving all the way up the sliding scale. Let's say we solve it tomorrow. Let's say that that's truth. Everything that ships is that way. We have long tail customers still using, and I say customers, not even GitHub customers, Git server implementations in places that have systems that are required to be 4 years old for airline requirements and so on. So just because it's solved, even if we do solve it, it doesn't mean that it's solved for the long tail of everybody using the system. So it's a durable solution. It's a good solution. So effectively, a compromise of balancing for file systems to make them a little bit happier by giving them a blend of files that are nicely balanced in folders, as opposed to 1 million in a single directory. I'll stay for more questions, but I think it's great to actually call that formally concluded. There's some prizes to give away, so I don't want to stand in the way of that. Thanks once again. You can ask me anything in the hallway. Thanks. Thank you.